Okay, so the key thing here, constant velocity, what does that make you think of, Todd? Okay, so it's going at the same speed, and then automatically that should make you trigger into thinking, what's your acceleration equal? Yeah, fantastic. What does that mean? It means your forces are balanced. Okay? Sorry, it looks like a 4-year-old wrote it. My pen is not real smooth today either. So let's look. Here's my free body diagram, and I want to make sure that you guys realize that you draw your forces out of that dot. That dot represents the center of mass of an object that's moving. So you're going to draw all the forces out of it. Sometimes you'll see pictures where it looks like it's pushing from the left and things. Those would just be like diagrams. Your actual free body diagram is going to have your forces come out of it. So here's this force that's pushing it along. It says it has a frictional force. So that's going to be equal because our acceleration is 0. So here's my frictional force. Then we know that we have the gravitational force, which is mg. And then we have our normal force because it's sitting on a table and that table's pushing back up, causing that normal force. So the number of forces that would be on that would be 4. You're pushing it, it's got friction. Those two are balanced so that when you do the sum of all the forces, let's concentrate on just the x direction. I would do the applied force minus the frictional force is going to be equal to the mass times the acceleration, but the acceleration is 0. So that whole side, the mass times 0 is 0. And what does that tell me? It tells me that my applied force equals my frictional force. So the number of forces would be 4. Good? Good? All right, all right, let's go to our next one. I'm gonna have that up there. Okay. Alrighty, so an object with a mass of m and a weight on the moon, while it is on the moon, where the acceleration due to gravity is 1.6 meters per second squared. What will the weight of the object be when it is brought to Earth? Will it be greater than, less than? What's true? So the acceleration due to gravity on the moon equals 1.6. What's ours? What's our acceleration due to gravity here on Earth? 9.8. How do we figure out the weight of an object? What's that equation? Here, it'll look more familiar if I say, oh, it's the force of gravity. You guys out in virtual range can unmute to make Todd feel like he has classmates. So he's not like on the hot seat here. How do we calculate this? Exactly, it's just mg. You guys knew that. So, where is it going to have a bigger weight? The Earth or Moon? Yeah, so the weight on Earth is going to be greater than the weight on the Moon. So that was a whole lot of talking, but that's typically what conceptual questions do. They try to make you think about things. But that would be proof. So if you got this wrong, for example, what I would be looking for is a good explanation so that I can tell that you really do understand the concept behind it, okay? All right. An object has a mass. Nope, we already just did that one, so there we go. I hope we get through all this. This is the one I thought number one was. All right, so let's go through the buzzwords here again. Here we go. Constant velocity should automatically trigger the idea that the acceleration is equal to 0 and that the forces are balanced. That looks like my pen warmed up a little bit. So when you add up all your forces, that's your net force. We know that it's going to be mass times 0, which means the sum of all the forces, or your net force, is going to be equal to 0. So it would have been this guy. All right. Now look, if you don't get it completely done, I am going to upload this. I'll do it to YouTube so you can like speed through it and get to the ones that you want. All right, so a large truck collides with a small car during a collision. According to which law? Which law is it?
Number 2?
Number 2? I don't remember what the question was. Do you have it?
It was the Earth question.
Oh, the one about the weight? The weight on Earth is going to be greater than the weight on the moon because our acceleration due to gravity is 9.8 and theirs is only 1.6. And we figure out weight by mass times the acceleration due to gravity. So that little g on Earth is 9.8. On the moon, it's 1.6. The mass stays the same. So that was the question, just making sure that you understood that the mass stayed the same, but the weight can change. And then, Nick, I'm going to upload this so you can see like whatever I wrote later today. So you can really make sure that you got it, okay? Good?
Thank you.
Okay, good. All right, so this is all about the third law. And when we were doing a review and stuff, remember I told you, remember that sentence. Like, go back and look in your notes for that sentence where I said, all you need to do is switch out the 2 objects. You're going to have 2 objects. Don't bring any more into it. But for example, this would say the truck puts a force on the car, then the car puts an equal and opposite force on the truck. So it's that third law pair, and it involves 2 objects and only 2. And those forces, as weird as it sounds, is true. That when they collide, they're going to have equal and opposite forces. Same thing, whether it's a car and a truck or a car and a bug, it doesn't matter. What stays the same is the force. What's different is going to be the masses and the acceleration. Like a teeny tiny mass is going to feel a huge acceleration. A big mass isn't going to feel much acceleration at all. But it's going to balance out mathematically to the same size force. Okay, so then that would be this force here. I mean, this explanation here. And it's always, you want to pick just 2 forces and just flip them in that sentence. Okay? All right. So Go back here. So an object with a mass m hangs from a string that is attached to the ceiling. The object pulls down on the string with the force mg. We're going to call that the action force. What's the reaction? So I just told you how to approach that type of problem. I want you to think about it, jot it down somewhere in your notebook, and then we'll see if you got it right this time. First, identify the two objects we're talking about. What are the two objects they're talking about? They are talking about the ceiling, but let's look at it here. The object pulls down on the string with a force. So even though the string is attached, what they're trying to say right here, the action force is the object pulling on the string. So the object and the string are going to be the two objects we're talking about. So then what would be the reaction? Anybody out in virtual world want to join Todd? So the object puts force on the string. Flip it. The string puts an equal and opposite force on the object. You could look at the string in the ceiling, but that would be a different action-reaction pair. You could say the string puts the force on the ceiling, and the ceiling puts the force equal and opposite that on the string. But that's not what they're looking at. They say the object pulls down on the string. So then the string pulls up on the object. Those would be third law pairs. And then we're still going to talk about action-reaction pairs in the next one. Action-reaction forces are always acting on different objects. So let's look here. Yes. So they're always going to act on different objects. So your goal would be to pick the two objects they're talking about and then just flip them. If one pulls up, the other one pulls down. If one pulls right, the other one pulls left. If one pushes right, the other one pushes left. So it's just those two objects. So don't let it get you clouded if you see multiple things, because that's what the questions they're doing. They're trying to test your knowledge. All right, let's get back. Here we go. A constant, non-zero net force acts on an object. What does non-zero mean? When we say this constant non-zero net force, we would say net force is anything at all except zero. Because if it were zero, then we wouldn't have any acceleration, right? Right? Yeah. Okay. So if it's non-zero, it could be a positive force, could be a negative net force. So it's not always going to speed up. Remember, the only way it's going to speed up is if it's moving in this direction and we have a net force and an acceleration in that direction. What happens if it's moving this way and the acceleration is this way? Is it going to speed up? It's going to slow down. So that would indicate a negative net force. This would indicate a positive net force. They're both still accelerating. It's just that's a negative acceleration. So this is your correct answer. And we definitely know that it's not going to move at constant velocity, because that happens when your net force, when you add up all your forces and it equals 0. It's just, you might have solved 0 and zeroed in on 0. Yeah, exactly. So you probably, and this is all just part of the practice of getting used to physics, and trying to do it in this hybrid situation is tricky. All right, let's see. Oh, this one was good. This has a whole bunch of info. So you have a horizontal force that accelerates a box from rest across a horizontal surface. It does have friction, and it's at a constant rate. So we have this force acting on it. You do the experiment again. Oh yeah, I did. Let's do number 8. Sorry about that. The force that keeps you from sliding on an icy sidewalk. What's going to keep you from sliding? Exactly. Static friction. So friction is going to keep you in place. It was so icy the other morning that, hold on, you don't. Okay, so friction opposes motion. So if you're about to slide out from under it, you want to make sure you do have some sort of friction. Number 10. Oh, I don't need to go into it. Here we go. So these are just like the tension ones we talked about, but constant velocity. What does that mean? You should automatically think A equals 0. The forces are balanced. Constant velocity. Now, just because it's moving up or down doesn't mean that the forces can't be balanced that way. It means that your Fg and your Ft are the same size. So the tension in the cable should be equal to the weight. I don't know what the exact choices are. Yeah. Yeah, so it would be equal to mg. And it would be a positive mg because look, it's pointed upward. Your tension's up. It's equal in size to the weight, which is pointed down. So that's why free body diagrams are super helpful, because they also give you the direction. If it's pointed up, it's positive. All right. You guys ready for the open-ended? I want to stress that full solutions, some still fight me on this. And yeah, it drives me crazy. So anyway, there was my lecture. Here we go. We have a stationary 15-kilogram object located on a table near the surface of the Earth. The coefficient of static friction between the surfaces is 0.4, and the coefficient of kinetic friction is 0.3. So we've talked about the difference between static friction and kinetic friction. Static friction is that frictional coefficient that occurs when you're trying to start to get to an object to move. And we did classwork and homework a little while back, but it should be in your notebook. And we said, let's find the maximum static friction first. And then we know that if I push on that object with anything less than that maximum static friction, it's still not going to move. Once it starts to move, then it's easier because our static friction and kinetic friction are different. The kinetic friction is lower. That's why our coefficient is lower than our static friction coefficient. That's what we did in our lab. Remember how in the graph, our static friction kept getting bigger and bigger and bigger and bigger until finally you get this object to move, and then it drops down, and then my kinetic friction is going to be less. All right, so here's what a full solution would look like. I would automatically say, here's the mass, 15 kilograms. Let's just write it there. I'll keep this all straight. My static friction is 0.4. My kinetic friction is 0.3. Automatically, I should want to make a free body diagram. I know that my normal force and my gravitational force are going to be the same. They want to know the normal force of that object. So part A, label your parts so that I know. You always start with an equation. So my normal force is going to equal my gravitational force. And then you would want to put mg. I know it's going to be mg, and then put your numbers in. 15 times 9.8 turns out to be 147 newtons. That is my normal force. Okay? I'm going to have an applied force here, and then I'll leave this as just a frictional. That can be static until we get it to move. Then once we start moving, it'll just be kinetic. All right. The maximum static frictional force. Static friction, well, friction I think we called it, is going to be mu f Fn. So my frictional force, you can put a little s there if you want to keep track of it, but this is part B. My mu s was 0.4. My normal force was 147. So my maximum static friction is 58.8. Part C is if 65 newtons of force is applied to a stationary object, what will be the kinetic frictional force acting on it? I even give you that as a hint, but it might have confused you because you might have thought, well, why would you tell me that? I don't know. But I'm telling you it's kinetic friction because I know I applied a force bigger than that. So hopefully me going through this helps you remember those problems that we did. We did a bunch of them. So how do I do this? Well, here was my free body diagram. Let me draw it real quick. now it's moving. So my friction is a little bit smaller. So if you want to specify, you can do that. Because remember, those equations are almost identical. The only thing that's different is the mu. And my mu here was 0.3 by 147. And the frictional force has gone down to 44.1 newtons. Now those are just the size of them. What direction are they pointing? Left or right? It's moving to the right. So which way is friction pointing? Left, right? So just keep that in mind with this free body diagram. It's here. This tells us the size of it. This diagram tells us the direction. That's why this is so important. Oh, did you? Did I catch it? For when we're just calculating friction, it's always the normal force. Yep, exactly. So it's almost identical. The only thing that changes is your mu. So your mu just changes a smidge. Or it could change a lot. It depends on the surfaces. But see how it's exactly the same. The only thing that's different is the number I put in for mu. If it's not moving and we're trying to get it to move, use static friction. If we already have it and we get it moving, then you figure out the amount of friction. Same exact way, except pop in the coefficient of kinetic friction. All right, I'm going to erase this. And then what is the acceleration of the object? Part D. Well, here I'm going to do my free body diagram again real quick. And that's Fn, and that's Fc. All right. When you want to find out the acceleration, you're going to do sum up all your forces and set them equal to the mass of the object times the acceleration. I look at my free body diagram just for the x direction. It's not moving in the y direction, so it's only in the x. So I pull it right off. My FA is pointing to the right, so it's positive. My F friction is pointing to the left, so I make it negative. And then I say M times A. My applied force was 65 newtons. My frictional, now it's moving, so my frictional force that I'm going to use there is going to be the 44.1 newtons. The mass was, what's the mass? 15 times A. So then you subtract those two and divide by 15, and you should get an acceleration of 1.3. Whoa, what happened to my pen? 1.39 meters per second squared. And in this case, we only had one force to the right, one force to the left. You're all good. If you take physics in college, you're going to have multiple forces. You're going to have forces that you're going to break down, but you're always going to look at just the x together with just the y together. All right, now we're into kinematics. So I'm going to erase this. And now I have my acceleration, and now I'm back to this idea that you guys, most of you have it pretty rock solid, except for your final, like showing me your work and going through. So it's all the details you have to polish up. And I'm pretty sure it started from 0. and it was going for 10 seconds. All right? Yeah. Okay. So I want to know how fast it's going after 10 seconds and how far did it go. Here's where you lose points often, by not writing the equation that you chose without any numbers in it. I need to know that you chose the right one. So even if you can do it in your head, that's not the physics. Like, that's just math. I need to know that you can do the physics. So for part E, it would look like this. I would write VF equals VI plus AT. Then I would go and I can put in 0 plus 1.39 times 10. I don't care so much if you don't put that 0. Like, that's okay. This, you gotta have. So then we know that the final velocity was 13.9 meters per second. And then part F is delta x is going to be equal to VIT plus 1/2 AT squared. You could have also used the VF squared equals VI squared plus 2A delta x. That would have worked as well, because now you have your final velocity. I chose this one just because, hey, just in case I messed up this, then I could still find this. The VI is 0, so that goes to 0, and then I would be left with this, plug in my numbers, and I would end up with 69.5. But my pen's not cooperating. Meters. That is a full solution. Show me what you know. Keep it neat, keep it labeled, keep it handwritten, scan it. And then if you go back to that, Kahoot is on there too. That will help you practice with conceptual questions as well. And that's about it.